What if the metals powering your phone, your car, and even green energy came from the bottom of the ocean? Today we are diving, literally, into deep-sea mining. Is it engineering genius or environmental disaster? Deep-sea mining takes place 4,000 to 6,000 meters below the surface. An area of crushing pressure, over 500 times what we feel on land. To explore these depths, engineers use ROVs and AUVs, remotely or autonomously operated submersibles, built to survive the abyss. ROVs, or remotely operated vehicles, are robots controlled by a human from a ship or platform above the water. It's tethered to the surface via a cable that sends video and receives commands. Usually it takes videos, collects samples, operates tools, like arms or suction devices, and performs inspections. AUVs, or autonomous underwater vehicles, are robots that works independently without being directly controlled. They are pre-programmed with a mission. It navigates on its own, collecting data with sensors and cameras. Usually they are used to map the seafloor, measure water chemistry, and survey for resources. The ocean floor holds treasures like nickel, cobalt, manganese, and copper locked in polymetallic nodules and hydrothermal vents. These metals are critical for EV batteries, electronics, and clean tech. But how do they get there? Polymetallic nodules formation is incredibly slow, happening over millions of years. First, the nucleus formation starts with a small object, like a shark tooth, shell fragment, or tiny rock on the seafloor. This acts as a nucleus for metal deposits to build around. Then the precipitation from seawater metals dissolved in seawater, like manganese, iron, cobalt, and nickel, start to precipitate out of solution. This happens layer by layer around the nucleus, a bit like pearl formation. After that, the phase of hydrogenetic growth takes place. Much of the metal comes directly from seawater through chemical precipitation, at a very slow rate, millimeters per million years. Then what is called diagenetic growth. Metals come from the sediments below the nodule. Pore waters, water and sediments, are rich in metals that diffuse upward and deposit on the nodule. This means that polymetallic nodules are layered structures that take place over millions of years by processes that create concentric layers of metal oxides. Slowly the nodule becomes rich in valuable metals. A well-known area called Clarion-Clipperton Zone in the Pacific holds billions of tons of nodules. Many countries have tremendous interest in this zone due to the large amount of nodules accumulated. Hydrothermal vents are cracks on the seafloor, usually at mid-ocean ridges, where superheated, mineral-rich water erupts from beneath the Earth's crust. Water seeps into the crust, heats up, often greater than 350 degrees Celsius, dissolves metals from surrounding rocks, and jets back out. When the hot fluid meets cold seawater, dissolved metals precipitate and form mineral-rich deposits. Harvesting these nodules requires advanced machinery such as hydraulic suction systems and robotic arms. But designing equipment that resists pressure, corrosion, and operates precisely on an alien terrain? That's where engineering shines. Hydraulic suction systems and robotic arms are masterpieces of engineering. The hydraulic suction system is like a giant underwater vacuum, designed to work in crushing depths. It uses powerful pumps to create a flow of water that gently lifts the loose nodules from the seafloor without stirring up too much sediment. Engineers have to carefully balance power and precision. If it is too strong, you create huge plumes of silt that smother marine life. Too weak, and you can't lift anything at all. Meanwhile, the robotic arms are like deep-sea surgeons. Mounted on remotely operated vehicles, ROVs, these multi-jointed arms are designed to pick, grasp, and manipulate objects with surprising finesse. They're engineered with pressure-resistant joints and corrosion-proof materials. After all, saltwater is famously unforgiving. Cameras and sensors guide their every move from the surface, letting operators miles above see what's happening in real time and control the arm as if it were their own hand. Together, these systems form an orchestra of engineering. The suction system collects scattered nodules in bulk, while the robotic arms tackle more delicate work, like clearing obstacles or picking individual samples. It's an incredible fusion of hydraulics, robotics, and remote sensing, all so we can tap into resources at the last frontier of Earth. Hydraulic suction systems, especially those used in deep-sea mining, are deeply grounded in fluid mechanics. Let's look at a few real engineering principles and math relationships they rely on, in plain terms. Bernoulli's equation. This classic fluid dynamics equation links pressure, velocity, and elevation along a streamline. As velocity, V, increases at the intake nozzle, static pressure, P, drops. This pressure drop creates the suction effect. In design, engineers adjust nozzle shape to increase fluid speed and create low-pressure regions that draw in particles from the seafloor. Continuity equation. If the nozzle opening, A2, is narrower than the hose, A1, the velocity, V2, must increase to conserve flow. This design principle lets engineers focus suction power right at the seafloor. Pressure head/suction lift. For a suction system at depth, engineers have to consider pressure differences. At 4,000 meters depth, pressure is almost equal to 400 atm, approximately 40 MPa. The suction system must be structurally engineered to withstand this ambient pressure, while maintaining enough internal pressure differential to draw material in. This presents a design challenge. Pump casings must resist collapse from outside pressure. Internal flow channels must maintain sufficient differential to move slurry vertically through riser pipes. This is the pump power equation, where P is the required hydraulic power in watts. Q is volumetric flow rate, m cubed per second. G represents the density of the fluid. Delta P stands for acceleration due to gravity, approximately 9.81 meters per square second. And H stands for head in meters. Engineers calculate how much power is needed to lift slurry up kilometers of riser pipe. Higher flow rates or greater depth equals more power. Head loss from friction. In long riser pipes, engineers must account for pipe length L, diameter D, flow velocity V, friction factor F. Higher friction losses means more pump power needed. Engineers optimize pipe materials and diameters to minimize losses. Practical engineering decisions involve sizing pumps for power needs, designing intake nozzles for optimal velocity and minimal sediment plume, selecting materials to handle corrosion and pressure, controlling sediment entrainment and abrasion. In short, hydraulic suction systems in deep-sea mining are a perfect example of applied fluid dynamics, pressure calculations, and mechanical design, all working together under extreme conditions. Once collected, the minerals are pumped to surface vessels through riser systems tubes using airlift pumps or powerful displacement systems. Think of it as an elevator for rocks operating under a mile of water. At the surface, these minerals are separated from seawater slurry on board ships. These ships are part mobile refinery, part chemistry lab, and part factory, floating in the middle of the ocean. But deep-sea mining raises serious questions. Sediment plumes can blanket fragile ecosystems. Some species may never recover. Engineers are working on solutions, but global regulation is still catching up. So, is deep-sea mining our next great engineering achievement, or a dangerous gamble with nature? Let us know what you think. Don't forget to like, share, and subscribe for more stories from the edge of science.